Analysis of finite state machines is the process of converting the logic diagrams of clocked sequential circuits that contain flip-flops that operate at a clock into a representation or a graphical representation that should help us understand what these circuits do. In this unit, I will show you how we analyze finite state machines by examples. I'll go and analyze each of these three circuits that we see in here one at a time, and we're going to try to figure out what these circuits do. In short, what I will be doing is I'll be converting these logic diagrams into state equations, state diagrams, and state tables, and hopefully the state diagrams and the state tables should help us analyze these circuits and understand what they do. So I'll start with this particular circuit as an example one. Okay, so this circuit here is shown enlarged. So this circuit has a couple of flip-flops. So it's a clocked sequential circuit because it actually utilizes these flip-flops, one in here and one in here. And both flip-flops in here are actually clocked. The clock is not explicitly connected, but it's implied that clocks are used. And I'm just not connecting them just so that declutter the figures. And all the figures I'm showing you in this module, they actually operate with a clock. I will just not show you that the clock is connected just for the sake of more neat graphs. All right, so we get started. So the first thing in analyzing a circuit like this is actually to write the state equation. So what is a state equation? Well, the state equation depends on the type of flip-flop. In the analysis process, I'm just going to go through D flip-flops. As you can see in here, I'm using 2D flip-flops, but the same process can apply to JK or T flip-flop. But anyway, what's a state equation? Well, a state equation is actually the equation that specifies the next state. What I'm trying to say is you should focus on these 2 points in here and write equations for those two flip-flops. So I will start by writing the state equation for flip-flop A. So this means that I have to write the equation that actually generates the next state. And what's the equation that generates the next state? Well, there is a little bit of a combinational circuit, not a little bit, but this is just a combinational circuit here at the input of this flip-flop. All I have to do is just write the equation that represents it. And the way we usually write it is we say for flip-flop A, the next state, you can just write A underscore next, kind of like what we do in coding, or we can just write, because we're writing on paper, is t plus 1 to indicate that it's actually the next clock cycle comes in. This is the value that that flip-flop A will have. So A t plus 1 is really whatever this particular circuit or this particular combination circuit actually tells us, which is the following. It's an XOR of what? Well, I'll have to follow this here. This is basically A, and I believe this is just B. So it is A, the current value of A, so I'm going to have to say A of T, XORed with the current value of B, okay? And the whole thing is ANDed with the current value of T here. Or X, sorry, not T, the current value of X, and X, by the way, is just an external input. So you can see that I'm using it in a couple of places in here. It's the same input. It's an input, and it's an external input from the circuit, and that circuit will generate an output Y, which we'll get to in a second. For the sake of brevity, so that we don't have like state equations that are too complicated, I will assume that it is implied that whatever comes on the right-hand side of the equation, or this is not an equation, this is more of an assignment. So on the right-hand side of the assignment, whatever comes in here is actually the current value. So I'll just ignore of t and of t and of t just to clean it up, because it is just implied that this is the case. So all I have to do is just, it's the current value of A XORed with the current value of B, and the whole thing is ANDed with the current value of X. And that will be the next value of A. And that's the state equation for this particular flip-flop. I'll keep the t plus 1 just so that I distinguish that this is the next value. And this is not a mathematical equation, it's actually an assignment here. All right, so we're going to do the same exact process, but we're going to do it for the flip-flop B, and all I have to do is just write whatever happens here in terms of the current states and the inputs. So what this tells me is B t plus 1 is actually just, I believe it's that one here, so let's follow this. This is not of B, and this is A. Okay, so we AND A, not B, or B bar basically, and or we can just do it's actually X bar, and that's basically the state equation for this B. And usually with the state equation we also write what we call the output equation. It's not necessarily a state equation, it's an output equation, but I usually include it in there too. So what I can say is Y, which is, you can say the next value or whatnot, but it's like Y of t plus 1. It is actually the, just in here it's just A, the current value of A ANDed with the current value of B. And that's pretty much it. And frankly speaking, there is no next value in here because this is not a flip-flop, so I shouldn't be writing that. It's just the value of the output, because the output is actually not a flip-flop in here. So all we have to do is just say that this is the output equation, which is the current value of Y. It depends only on A and B, at least for this particular circuit. All right, so this is the state equation, and this is the first process in analyzing a finite state machine. So next state is actually what we say, let's write the state table. And there's a couple of ways to write the state tables. I'm just gonna focus on this one first, and then we'll see the next one. So what's a state table? Well, a state table is just a table that contains 4 sections usually. So it contains the present state, an input, a next state, and an output. What is the present state? Well, usually you list under the present state all sorts of flip-flops you have. So according to this diagram in here, I have a couple of flip-flops, a flip-flop A and a flip-flop B. So that basically shows me that I have A and I have B. And I also write all the inputs. In this particular circuit, I only have one external input, and that's X. If you have more, you usually write them here. So that's the first thing. We're going to get to that in a minute. It's actually just a different representation of the same table. I'll just build it in here, and then I translate it to the other one and show you the differences. All right, so what's like now we know what this present state and next state, well, the present state is the flip-flop. The next state is actually the same flip-flop, but the next value on the next clock cycle comes in. And of course, we do have the output or outputs, depending on how many outputs you have. This circuit is just giving me Y, so I'm just gonna say Y. All right, so the next state in actually writing the state table is actually we have to list all binary combinations of the present state and the input. So it's kind of like a truth table. So what you do is you say 0, 0, 0, and then this is a 1, and this is a 2. Okay, it's basically you can write it like a truth table, 0, 1, 0, 1, 0, 1, and then a couple of ones, a couple of zeros, a couple of ones, and then 4 zeros, and then 4 ones. All right. So how do I write the next state? Well, there's a couple of ways you can do it. You can either depend on these state equations that you just did, or you can just take a look at the diagram and figure out what the next value is based on the diagram. However, I do find it easier to use the state equations, and that's why I wrote them. So what I'm going to do is I'm going to copy them, and I'm just going to paste them here so that I don't have to scroll up and down. And this will help me figure out what I need to do. So what this is telling me is the following. The next state for A, which is this one here, this is the equation that happens. This is basically depending on A, depending on B, and X. And really what I'm saying is it has to be A, X, or B, which are the current values, and ANDed with an X. And of course, anything ANDed with an X, and if X is 0, it's going to be 0. So whenever X is 0, I'm just going to write 0 just to go ahead with that. And next, what I'm going to do is I'm going to say, all right, so if X is 1, whatever happens in here will appear at the output. So I'll have to figure out what these are. And these are just the XOR of A and B. So in this particular case, it'll be 0. And this here, it'll be 0 and 1. That means the output is 1. This is 1, and this is 0. And now I figured out what the next state of A is based on the state equation for A. I can do the same exact analysis for X in here. So X in here is telling me it's A, B prime plus X prime, as you can see in here, plus X prime. So because it's a plus X prime, this is actually just a normal OR. Okay, so OR, whenever X is 0, that OR will give me a 1, like X is 0, that means X bar is 1. Whatever you OR with a 1, it has to be a 1. So I'm going to just say this has to be 1, this has to be 1, this has to be 1, and this has to be 1. And these are based on these values in here. All right. Now, next, what I have to look for is the A is 1 and the B is 0. So I'm looking for, this is a 1, 0. Well, I can go like 1 by 1. This is 0, this is 0, this is 1, and this is 0. And I figured out the next state for B now. So that leaves me with the output, and the output is just based on the current state, not the next state. So I have to take a look just at the present state. Again, usually we look at the input and the present state to figure out the next state and the output. So this just tells me that it's the AND of A and B, which is technically just 1 in here and here, and the rest of them is just 0. All right, so that's the state table for this particular circuit. You might find it in some books or some websites that the state table is written a little bit differently, and the way it's written differently, it's just a reorganization of the same state table. So you usually see a present state or the current state, And the next state will be split between x equals 0, that's the input, and x equals 1, which is also an input. It's like if you have multiple inputs, you're going to have more of these arrows or columns. But anyway, so this one here, it's technically, it's telling me let's just focus on x of 0, or let me just do it that way. So we're going to write the present states. This is 0, 0, this is 1, 0, this is 0, 1, and then 1, 1. And now I'll have to figure out what's the next value of a when x is 0. So I'll have to take a look at this a in here and just do that, this a in here and just do that, this a in here and this do that, and this a in here, and I can write it here. Of course, I can just fill out this from the start. So I know that anything that is ended with a 0 has to be 0. So all of these are actually zeros. So I can technically, I'm saying you can use the state equations to fill the state tables. All right, so what about if x is 1? If x is 1 in here, so that a will be just the XOR of the current value of a and b. So technically that will be just an XOR. That means this is how an XOR is written, an XOR of these two in here. So I filled out these, and you can track it. I basically have the same, and like a quick check is like, well, I have a couple of ones in here in total, and in total I have just a couple of ones. Just a quick check. Let's do the same thing for b. So for b, it's telling me whenever x is 0, everything has to be a 1. So all I have to do is just say 1, 1, 1, and 1. All right, and then here it's telling me I'm looking for a is 1 and b is 0. I'm looking for a is 1 and b is 0. That's the 1, and everything else will be 0. All right, and the final one in here is just the AND of a and b, which is here. So all I have to do is just write 0, 0, 0, 1. And as you can see, chances are this is a little bit easier to write, and I find it a little bit easier just to follow sometimes, but either way is fine. All right, so the next state in the analysis is going and drawing the state diagram. Okay, and the state diagram, we usually can base it on the state table. So what I will do is I'll just copy this guy here. Okay, so we're gonna copy it, and what I did is I just placed it in here, so I free up some space in here. All right. So how do I do the state diagram? And the state diagram usually is the human way of interpreting the purpose or the reason for that particular circuit we're trying to analyze. So what I usually do is you can definitely keep it as zeros and ones. There's nothing wrong with that. I usually rename, for example, my states. So these ones here is 0, 0. So I usually would call this, for example, this is state 0. Let me just write it. So this is state 0. This is state 1, this is state 2, and this is state 3. You don't have to do that. Sometimes you're going to see the diagram has zeros and ones instead of states, but I just find it easier to do that. And the reason why I find it easier to do that is the following. So for every state, I have 4 of them in total. Okay, we're going to have to draw a circle. Okay, so this is a circle for S0. Okay, and this is a circle for example, S1, and this is a circle for S2, for example, and this is a circle for S3. So each one of them will contain a state. So instead of S0 or 1 or 2, I could have just written 0, 0 in here, 0, 1, and then 1 and 0, and then 1, 1. The same exact thing. So how do I construct the state diagram? Well, I'll take a look at this table in here. It's telling me, well, if you are in state 0, let's focus on this state first. If your input is x is 0, your next state is this particular case in here, which is a 1. So all I have to do is just do a transition arrow. So this is the transition arrow, and I usually write on top of it whenever the input is 0. If you have multiple inputs, for example, you have x1 and x2 and x3, you just put a comma, for example, and do the other ones, like if they're 1 and 0. But anyway, for this particular case, I only have one input, so that's all I care about. Next, I can usually take a look at S0. What about if x is 1? Where does it go? Well, it stays in S0, so all I have to do is just say, well, I'm going to stay, if the input is 1, I'm going to stay in the same situation here. The same goes in here for S1. I can see that if the input is 0, the state stays in the same place, which is 1. Okay, other than that, if actually the input is 1, I'll go to state number 2. That tells me that here is whenever it's 1. So I'm going to go to state number 2. It's telling me you either go, if the input is 0, you go back to 1. So this one here, I can just do that here. This is 0. Or if the input is 1, you go to state number 3. This is the input is 1, you go to state number 3. Okay. And now I have the final state in here, which is state 3. It's telling me the next state will be state number 1, which is this one here, if the input is 0. Or you can think about it like the next state will be 0 if the input is 1. So you can just do this in here. So that describes this particular part of the table, which is the current state and the next state. So the next state will help me just figure out the transition arrows, and they're all based on inputs. So in this particular circuit, it has an output, and this output only depends on the current state. So you don't see any inputs or outputs in here. They don't get affected. Even if you look at the alternative style of this table, you're going to see that it's basically replicated. These ones in here based on x0 and x1, they're the same, and they're the same, and they're the same, and they're the same. They don't depend on x. And you can take a look at the state equation in here. You're going to see that y does not depend on the input at all. You'll also take a look in here. You can see that y only depends on the current state, and this x here does not appear in the y. Okay, why does that affect it? Well, this is a type of Moore machine. We're going to go to the details of between the differences between Mealy and Moore. But for now, this is just a Moore machine. So if it's a Moore machine, the output does not depend on the input. So usually you take a look and you usually write it inside those circles. You can tell me what the output is inside these circles. So, well, taking a look at that, it tells me that y is 0 at S0. That's what this is. And it's at state 1, it's 0, sorry, and at state 2, it's actually 0. And state 3 is the only one where it's 1. So you usually write 1 in here, 0 in here, and 0 in here. And now my state diagram is done, and I can try to interpret what is this particular circuit doing. So let's now try to at least analyze what this circuit does. Well, let's assume that we start with S0. What this circuit does, it actually looks for a pattern of 1s and 0s. So if the input is 0, followed by a 1, followed by a 1, I'll get this output 1. So technically, if you get a 0, followed by 1, followed by 1, I'll get the output y to be equals 1. Let's see. What if happens like if I veer a little bit differently from this particular pattern? For example, if you go and say 0 in here, you go to that one, and then you get another 0. So you get stuck in here. So 0, 0 will not output anything. Now, if you keep getting 0, if you keep getting 0, that's it. So technically, this state here, you can think about it as storing the value at 0. So I've seen a 0. That's what S1 stands for. Now we can go to the next state in here. If the next value is 1, you can see that I stay in here. So technically, I've seen a 0 followed by a 1. That's what state 2 stands for. So I saw a 0 followed by a 2. So now if I see a 0, I go back to here. Well, I've seen a 0, and that's it. And you stick in here till you see a 1. So when you see a 1, you go to state 2. So you can write these on the side, for example. You can tell me, well, S1, I've seen a 0. Well, S2, I've seen a 0 followed by a 1. That's what this state means. And usually with experience, this isn't the only way to do it. This is just my experience and the way I'm interpreting this particular diagram. But anyway, we continue. For example, S2, if you see another 1 in here, you're going to see that pattern 0, 1, 1. And you can say, well, S3 remembers that I've seen 0 followed by 1 followed by 1. Now, what happens if you get another 0? Well, if you get another 0 after the S3, it goes in here. It's basically that particular state, which is I've seen a 0. And you go from there. So if you've seen a 0 followed by 1 followed by 1, you're going to get a 1. Good. What about if I saw a 1? Well, you're going to see that S3 actually goes back to S0. And S0 is just I've seen a 1. And you can take a look at that. I didn't see anything that I've just seen a 1, not followed or nothing like next to it. So it's just a 1. And that's how it is. So what does this circuit now do? Well, what we did is we started with the diagram. We wrote a state equation in here, and we figured out that state equation, we figured out the state table out of it, and then from the state table, we converted it to the state diagram, and that's usually the state diagram is the human way of interpreting what that circuit was doing. And we figured out it actually is a circuit that interprets a pattern of 0 followed by 1 followed by 1.